Hello everyone, welcome to the lecture of analog communication. After today's lecture, you will be able to illustrate the time domain and frequency domain representation of single sideband suppressed carrier signals. Now, for the sake of simplicity, let us start with some single tone signal. Okay, or in other words, I can say that we are dealing with single tone modulation system. Now for that, we consider basic signal mt to be Am cos omega mt, and if you take its Fourier transform, it will give you two shifted delta functions, as you can see. So if I consider graphical representation, this is the time domain representation of the message signal, and you can see two shifted delta. One is at plus Fn, another is at minus Fn. Again, we are considering carrier Ct to be equal to AC cos omega Ct, that is equal to AC cos 2 pi fct. So again, if you take Fourier transform, you will be getting two shifted delta functions. So you can see this is actually the carrier signal, and this is actually the frequency spectrum. So one delta appears at plus fc, another at minus fc, and as you know that carrier frequency is higher than the message frequency. So you can see Fc appears at a higher value of A. Now, if we consider double sideband full carrier DSB Fc, as you already know, that it can be represented as AC plus Mt cos omega Ct, where Mt is equal to Am cos omega Mt. Now you simplify this expression. After simplifying, you will be getting DSB Fc modulated signal as AC cos 2 pi fct, Am cos 2 pi fct into cos 2 pi fmt, and if you further simplify, you will be getting three terms. So one as AC cos 2 pi fct, another is Am by 2 cos 2 pi fc plus fmt, and third one is Am by 2 cos 2 pi fc minus fmt. Again, if you take the Fourier transform or frequency domain representation of the double sideband full carrier signal, for this you will be getting two shifted delta. So you can see delta f minus fc plus delta f plus fc. So in this figure you can see this one is for delta f minus fc, and this one is for delta f plus fc. If we take Fourier transform of this, we are getting delta f minus fc minus f and delta f plus fc plus f, and we will be getting this and this corresponding to this pair of deltas. Similarly, if we consider this term Am cos 2 pi fc minus fmt, I am getting these two terms, Am by 4 delta f minus fc plus fm and delta f plus fc minus fm. So these two deltas are represented by this and this. Now this is all about double sideband full carrier. But again, when we are going to design a communication system, two important parameters that are to be taken care of are transmission power and transmission value. If you can see double sideband full carrier, here you can see that this particular term is transmitted along with the information, but it carries nothing. So transmission power is high. And if we consider transmission bandwidth, again in this figure you can see this is actually the bandwidth, which is twice F. So you want to reduce this. So if we consider double sideband suppressed carrier, of course there will be some reduction in transmission power. So in that situation, we are going to actually remove this term. We are going to remove this term. So that means here we are going to remove these two terms. Correct? In other words, I am not going to send this term. I am not going to send these two terms. This term, right? So what I am getting is actually we are going to transmit this term. multiplied by this term. That means when we are going to consider double sideband suppressed carrier, we are actually multiplying MT with CT by using some product modulator. So this term will now appear as AC cos omega CT into AM cos omega MT. So now I have this, I have this, I have this. So now you can understand the corresponding frequency domain representation will be this. As I have already removed the carrier, so transmission power will be less. However, bandwidth remains same. So, if we consider the corresponding time domain representation for double sideband suppressed carrier, you can see that it will look like this. Okay. So, by this method, you can actually reduce transmission power to some extent. And if we consider transmission bandwidth, there is actually no reduction. But now, if you look into this situation, that if you have this point as FC, this FC plus Fn, and this FC minus Fn, these two actually reside symmetrically above FC, and both are carrying the same information. Then what is the need to send two terms simultaneously? I can actually eliminate any one of them for the sake of simplicity. Again, let me consider that I am sending only FC plus Fn. That means I am now removing this. I am removing this. So now I have only this and this. So if we actually look into the expression, then what I am getting? What I am going to get? In this situation, I am going to remove this term, these two terms, right? That means I am going to remove this term, right? So here you can see that if I have only SSB signal, if I consider SSB signal, I am only going to transmit. I am taking amplitude to be equal to 1. So I am going to transmit only cosine 2 pi fc plus fn into t if I consider only upper sideband transmission. And corresponding to this, I will be having this. So you can see that again transmission power is reduced by half with respect to double sideband suppressed carrier. If we now consider transmission bandwidth, now I have only one particular sideband. So now the bandwidth is reduced to half. That means here bandwidth becomes Fn. So in this way, when we are going to consider SSB, I am actually saving transmission power. I am also reducing the transmission bandwidth. Of course, when I am going to do this, the complexity of the communication system will increase. So let us now have a look on the time domain SSB signal. So you can see this is nothing but this cosine 2 pi fc plus fn into t. That means now frequency increases to some extent if I consider upper sideband transmission. So now you will be getting simply a cosinusoidal signal with its frequency is slightly increased by Fn. Okay. Of course, if I consider lower sideband in that situation, we should have cosine 2 pi fc minus fn. In that situation, we will be having slightly reduced frequency with respect to the TNTL frequency. Okay, so what I have discussed is all about single tone SSB modulation. With this knowledge, you can formulate SSB SC modulations schemes for any generalized signals. So you can start from any message signal MT, and then you can apply Hilbert transform, and then you can proceed to actually obtain the generalized expression for SSB SC signal. Thank you. ঠিক আছে, হ্যাঁ যা হয়েছে স্টপ পজ হয়েছে ক্যান্সেল হয়